So, good morning. Welcome to Krishna's class. We shall continue with our building up of the strategies to modify Riemann integral and to introduce the concept of Lebesgue integration. We have done most of the work already. We have seen that one of the crucial points in our strategy is to approximate the function from below through step functions. But step functions now defined on a larger class of sets than intervals, because you see that in the Riemann integral the step function that we have defined was conforming to the partition that we introduce on the domain. But that is not, it's the same strategy that we use, but then irrespective of what function was, we were working with the class of step functions defined on partitions of the interval. So you get only intervals there. Okay, right? So the domain is partitioned through what are called disjoint intervals. And then on that we define step functions. We try to approximate the function from below as well as from above from using this these step functions. And if the area computed using the step function, the step function approximations from below and the step function approximations from above turn out to be equal, then you said it is Riemann integral. Now this was our strategy. Now what we have done is, we have gone to introduce a larger class of subsets of the domain on which we define the step functions. Because to allow a larger class of functions to be brought under this integration, that is, we want to include functions which may take infinite value also on some sets. We got rid of the idea of approximating from above, because such approximations in our strategy will give only infinity. So that doesn't help. On the other hand, we approximate from below. That means the step functions are bounded by the given function. Stay below this. And then what we do is take the pullback of intervals from the range of the function. Okay. That provides us with a large class of subsets. When you use two disjoint intervals and then take their pullbacks, what happens is that the subsets that you get on the domain are also disjoint. Certainly they are not necessarily intervals. It could be a union of intervals. It need not be even union of intervals, as we have seen working with what is called the Dirichlet function. So all sorts of subsets may arise from there. And now we are forced to introduce the notion of length for such sets. Now that is the problem. So let me just recall. So this was our strategy. We had, I'm just taking the interval AB and a non-negative function, and you have already seen that it is enough to work with non-negative functions. And you have, see, suppose the graph of the function is not necessarily continuous function, but something else. And then if you take yi minus 1 yi, the pullback of this turns out to be some set here. So the pullback under f, so this is the function, and we are working on what is called the pullback of this. This is f inverse of yi. And now, with respect to the partition that you have, the partition is going to be 0 less than or equal to 0 equal to y naught. And for this partition of the range, now that's important. So you have a step function constructed, which we designate by Sx, you define as sigma I equal to 1 to infinity yi minus 1, that is the minimum value that it takes on the interval, yi minus 1 to yi, f inverse of that means you approximate on this set the function by its minimum value yi minus 1. And likewise you construct a step function. Now the step function is well defined, may not be able to picture it, but in the case of general functions, but in general you will get a relation like this. And what we hope to do is this. So we are going to introduce a notion of length for this, which we designate by m, and m is what you call the measure. So we want to get this in this form, or we define it in this way. Once m is well introduced, 1 to infinity yi minus 1 okay, this is the characteristic feature. Sorry, I think I wrote the wrong thing, so let me just correct it. Sorry. I made a mistake. What I do is this: yi minus 1 into the characteristic function of f inverse of I minus 1 yi. Now the integral of Tm is defined as yi minus 1 into the measure of f inverse of that, of course, sets the task. The task is for subsets of the domain we want to introduce the notion of measure. And you see that suppose wherever the function is or suppose the function is a monotonically increasing function, then corresponding to the partition that you introduce on 0 to infinity, that is the range, the domain also get partitioned into intervals, and then of course Riemann integration idea works, and there of course everything is well defined. The measure of f inverse of yi minus 1 by I has to be the length of whatever interval. This is an interval, then it is the length of the. Otherwise, but in general, this need not be an interval, may not be even a union of disjoint intervals. Because if it is a union of disjoint intervals, then you can extend the notion of length from an interval to the measure of this set, which is the union of disjoint intervals, as the sum of the lengths of these intervals. That is possible. That is the natural way in which you can extend it. But then we have seen that in that Dirichlet function case, we have seen that it is quite possible that this set need not be even a disjoint union of intervals. Okay. So you will have to, if possible, you would like the notion of length to be defined for every subset of the domain and investigate whether that is possible. Okay, that is one problem. So one problem is, if possible, introduce the concept of length, which we shall call measure, for every subset of domain. At this stage, I am cautious. I have used the word if possible. But we would certainly like to introduce this. And that second, such a measure that you introduce should coincide with the usual length. If f inverse of, okay, if the subset of the domain is an interval, then the measure of that set should coincide the usual notion of that term. So that's our task. A third property is that If the set is a disjoint union of countable measurable sets, then the measure of the set should be the sum of measure of each of the disjoint collection. That is, if An is contained in the domain, generally let us take this to be equal to R. Yes. And see, they are disjoint, pairwise disjoint for every m not equal to n. That means they are pairwise disjoint. Then measure of is defined and measure of so this should be the sort of function that we are looking for. Okay. You just change the, it is, I don't want to use m for anything else. It's I not equal to j, this is all. Yeah. This property should be, is desirable to satisfy. So we want the measure to be this. So in short, this is what we are looking for. Okay. So it should be, this is expressed by saying that measure is a countably additive set function. Okay. So that's a desirable property. Right. So let us now work out further. If drop the condition such that I not equal to j, then measure of union I equal to ai all these are suggested with intervals. Okay, so we want all those things to be retained by this class of functions, and intervals should belong to this class, and every interval belong to this class collection of measurable sets and measure of equal to the length of the interval. So for intervals, the measure and length concept should be same. Now this is our task. Okay. Therefore, how do we proceed? The first observation that we make is that the class of subsets that you take up has some structure, because we are now not interested in just one function, but on a whole class of functions which are possibly coming under this integration process. Okay. Therefore, we shall work with a class of subsets. So let A be contained in what you call PR, is a subcollection of R. PR is the subsets of R. What kind of properties that we demand for A? This could be the whole of PR. Okay. then one empty set collection. 2 A belongs to this collection implies A complement. The script A. The third property that we ask for is this. Collection of subsets then we would like to have union that means the union of any countable collection of subsets belonging to script A should also belong to script A. Now, some of the consequences of this are the following: that the whole set if countable subcollection of A, then intersection belongs to. So both these things are there. This is easy to see because if you take phi for A, then you see that phi complement is the whole of A. Therefore, by 2 the condition 4 is valid. And if you go for the intersection of this, okay, take the complement of this. The complement of this is in A. Complement is given by intersection n equal to 1 to infinity a n complement. A n complements are all what are called measurable functions, or all belong to the class A, and therefore you see that this also can read out from that problem. So that is no problem. Okay. So we shall call sigma or script a sigma algebra of subsets of So this appears to be the class on which we have to define the measure, which is a set function. Set function in the sense that the argument of this function seems to be sets. Okay. So that, see, what you have is this: M is a map from script A into R star. M also could be a extended real valued function. So this is what we are looking for. These three properties really are crucial consequence of this. Okay. Now it is quite possible that, so the question that you ask is this: is A equal to well, PR is a sigma. Then there is a problem. If we are taking PR as a sigma algebra, there is a question of, there is a restriction that we posed, namely that if you have a countable collection of subsets which are disjoint, the union, the measure of the union should be equal to sum of the measures of the sets. Now, that's a restriction that we are putting on the function. Therefore, it is a valid that if it becomes PR, then all our problems are over. If everything works, that is so here. But the problem that we encounter is defining a set function which is countably additive, and also translation. Why translation weighted? Because you know that intervals are translation under the length function. Which is countably additive, and translation weighted. That is, we want these two properties to be AI whenever J. And we also want this property to be true, namely that M of A plus X. This is the translation. We know that this is a property that the interval with length function satisfies. So it's not that any function you introduce on this collection has to satisfy. It is desirable that these two properties are also true. And with that, if you ask the question, can you choose A as PR, maybe or may not be true. At the moment, we shall not bother about it. Okay. With such restrictions, is it to have A equal to the set of all subsets of R. This is the problem. See, it's not any function that you define. You are defining a function on subsets such that when the subset becomes an interval, it should coincide with the length. Okay? And therefore, you would like the function that you define to have the basic properties of this length function. You know that if you have disjoint intervals, then the way in which you extend the concept of length, which seems to be the reasonable thing to do on this set, on the union of these intervals, if they are disjoint, then is to take the length to be equal to the sum of the lengths of these intervals. I mean, that's a natural thing that you do for that. So that should be, that's the one that is captured here in a more general way. Another thing is, if you take an interval and translate it, the length does not change, and that is the translation invariance problem. So the function, the length function that you introduce should have in general this property. Therefore, we desire this also to be true. Now the question that you ask is, with all this, is it possible to have script A equal to PR? Let us keep this question in our mind. Therefore, we don't care at the moment that A is the script A is, that is the sigma algebra that we are going to work with, is the whole of all the subsets of R, or a proper subcollection of that. Maybe, we don't know. But certainly these properties are to be, the basic properties of A are to be satisfied. Okay. So we shall not bother about it. So let us postpone the answer to this question for a later discussion. We shall postpone this question for later discussion. Now we make some observations. Suppose collection of subsets of R designated by S. But on S we are not assuming that this is true. So then what you have is this. There exists a smallest sigma algebra Well, this is a powerful result. I mean, it's quite easy to prove because you see that the proof goes like this. S is certainly a subcollection of ER. And this is a sigma algebra. So there exists a containing now suppose you take two sigma algebras. Let B1 and B2 be two sigma algebras containing S. That is, S is contained in B1 then since S is contained in both B1 and B2, B1 intersection B2 is non-empty. Now you have to show that this is a sigma algebra. That is quite easy to prove. B1 is a sigma algebra, B2 is a sigma algebra. Use that to show that B1 intersection B2 is also a sigma algebra. So all the properties required of this are satisfied. For instance, if empty set belongs to both, therefore this you have to show that this is a sigma algebra. So show that B1 intersection B2 is a sigma. Now take the intersection of all sigma algebras containing S. Then their intersection is a sigma algebra meaning see in the worst scenario you have PR as a sigma algebra, so it is an non-empty collection. So you take this, then the collection of sigma algebras, or the intersection of any two sigma algebras is a sigma algebra. Intersection of any collection of sigma algebras is a sigma algebra. Therefore, you see that, and each of this would contain S. Therefore, it would S also is a subcollection belonging to the intersection. Okay. And this is the smallest sigma algebra so there exists such a sigma. So you are comfortable there. All these little results give you some comfort. Okay. Now what about the function M? Okay. Right. So we shall work with, okay, what is the significance of this? See, we would like the sigma algebra to contain a given collection of sets. For example, consider all open subsets of R. We would like a sigma algebra to contain all open sets. Okay? Therefore, what you do, the collection of open sets as such may not be a sigma algebra. But then there exists a minimum, a smallest sigma algebra that contains this collection. So that will take care of that. Okay, right? And our objective is to define the measure for all those elements in the minimum sigma algebra that contains these open sets. Okay, right? So that's the objective. That's the reason why we look for this such a collection. Okay, or the what you call the minimal sigma algebra. So we have comfortably proved that there exists a smallest sigma algebra containing S. S may be any collection of subsets. Example. S set of all open sets. So we would like to this sigma algebra. For example, you see the reason for this, I'll once again work on this. Suppose you are talking about a continuous function defined on R. Okay. What does the continuity mean? The continuity means that if you take any open sets in the range, its pullback should be an open set in the domain. Okay, that's what you mean by the function is continuous. Therefore, you see that if you are to define the integral of a continuous function, then you should have this property that the pullback of any open subset of the range in the domain should be a element of the sigma algebra, so that you can define the m function. That's the reason. And in fact, this is, therefore, if you were to work at least with the minimal sigma algebra that contains open sets, that would give you a good collection on which you can define it, and it also assures you that the following, namely all open intervals are in it, and therefore you can use this property to show that the closed intervals are also in the corresponding minimal sigma algebra. So that is possible. And what is the consequence of all this? The consequence of all this is that all continuous functions come under your definition of integration, or all continuous functions would become integrable in the new sense in which we are defining it. That's a great advantage that we get. As you know that all continuous functions on bounded intervals are, or compact intervals, are Riemann integrable. Okay, so certainly you need, you would like at least that much to be true. Okay. So that's just an example. So you, depending on what kind of integral you want to work on, see, you can fix the set of functions, the minimum requirement of which sets you would like to be in your sigma algebra. So that is possible. And once you have that, then you see you are able to write down the integral. As I said, if Sx sigma y I minus 1 I equal to 1 to 50, yi minus 1 f inverse of, or the characteristic function of f inverse of yi integral Sx Pm to be equal to sigma I equal to 1 to infinity yi minus 1 to be with the measure of f inverse of yi minus 1. This is the strategy. So that is the integral for the approximity. And you see that you would like the following property, that is limit Sx, okay, limit Sx, or you call the partition P, okay, where the partition is of course the y naught. So P you take as so for this partition we are writing this. Now you refine the partition, okay. When you refine the partition, you, as I have said last time, this SP start moving upward. That means you get a monotone sequence, and this monotone sequence either would converge to a, at each point it will converge to a value, or that means it will define a function which may take infinite values at some places wherever this sequence diverges. Okay, so that's a different thing. Okay, for each x you will have to work. Now the integral, accordingly, the integral that you have defined here as the length of the intervals go to 0 would be defined as, would go to a finite limit or infinite limit, becomes infinite. Accordingly, we define the integral of f as the limit of this integral. So we will taken over P of this is what you call the Lebesgue. Okay, right? And you can show that if f is Riemann integrable on a some bounded subset of R, then you can show that the Riemann integral and the Lebesgue integral coincide. So that means this would become a genuine extension of the Riemann integration theorem. Okay, so that is the strategy that we adopt to define the integral. Now I want to make a remark. When we worked on Riemann integral, the step function we defined were on intervals. Okay. Whereas here, the step function that you define is not necessarily on intervals, but also contain all sorts of subsets, because we are going to have chi f inverse of yi minus 1 yi, which may not be even an interval. So this f inverse of yi minus 1 yi may not be an interval. Okay, the step function that we define is now on a larger class of subsets. This is the advantage. And this larger class is constructed with the help of the given function. Therefore, in this integral, see, that's one very, very important difference. Okay, the step function. In the other case, the step function would involve the supremum and infimum of f on the interval. But that apart, see, the partition is the partition that you take of the domain does not involve. So in the Riemann integration, the partition that we consists of intervals which has nothing to do with the function, independent of the function that we are working. That is, f has no role to play in constructing these intervals. So we have this equation a equal to x naught, x1, and then throughout the working, we need only work with the length of xi minus 1 to xi for the values of I that come. Okay. Whereas now new integral we obtain or construct a partition of the domain with the help of the function. And you see, given by f inverse of this gives a partition. The domain is partitioned using this, and you see that if you take the union of this will become the whole of range. Okay. Where of course each of this need not be a may be an interval or may not be an interval. That is why we need to extend the notion of what is called length. Okay, but point I want to emphasize upon is this: the partition that you devise is constructed using the function. So the function has a given function has a significant role in getting the partition out. And this gives a substantial leverage. So to include functions not Riemann, also brought this new integration theorem. On the other hand, we are able to show that RAB integrable under the new integral with the integrals coinciding. I just give an example. I conclude with an example that we have considered, that we know that the Dirichlet function is not Riemann integral, but we show that this can be brought under the new regime. The Dirichlet function chi of is not equal. But this is a sort of step function. Okay? It is 1 on 0 1 intersection Q, but F takes only two values, 0 and 1, and integral f dm is equal to 0 into or 1 into the measure of this one plus 0 into measure of this is the set of all irrationals. Okay. On the set of all irrationals, the function takes the value 0, whereas on the set of all rationals on the interval 0 1 it takes a value. Therefore, this integral is 1 times the measure of this set plus 0 times the measure of this set. And this, of course, is 1, 2. You can show that the measure of this set is 0. Therefore, this is 0 plus 0 into 1. This is Riemann integral, but this is not. This is Lebesgue integral, but it's not Riemann integral. Okay, so you see that you get functions which do not come under the Riemann integrability also get under the new regime. Now this is the advantage. So I think that gives an overall picture of what strategy we are going to use. Now our job is to do a very rigorous development of these ideas. I have not used any rigorous thinking on this, but you should realize that we have to make all these quite rigorous, and at each stage whatever we are doing will try to get justification from our requirements that we have discussed. So with this, let me stop these discussions on the strategies. So that more or less completes what Lebesgue integration is all about. Okay. Right. Okay. So from the next stage onwards, we will be working on what you call define what is called Lebesgue measure, and then introducing later on and looking at the properties of the Lebesgue measure and how to get the Lebesgue measure for say as large a class of sets as possible, etc., etc. So thank you very much. Let me stop.